Hello guys, welcome on Tesla Adventures. In this video we are going to discuss the Poiseuille equation and the volume rate flow through a pipe. Let me tell you what I am talking about. Just imagine a pipe which is containing a flowing liquid, and obviously in most of the cases the liquid flows in laminar flow through the pipe. And laminar flow means that through the pipe liquid flows into cylindrical layers, each layer having the different velocity. So let us suppose that in this case obviously the velocity gradient is non-linear, so we cannot assume that the velocity gradient is linear. So let us assume that this pipe contains a liquid which is flowing with a velocity v0, and this v0 velocity is the velocity of the layer which is just on the axis of the cylinder. So all the molecules of the liquid which are on the axis of the cylinder are moving with a constant velocity of v0, and v0 is constant. Okay, so all the different molecules at different layers will have some different velocity obviously. Now the liquid which is pushing this liquid inside the cylinder from behind is applying a pressure of P1, and the liquid which is ahead of this cylinder is applying a pressure of P2 in the cylinder. So we have to find out the volume rate flow of the pipe, and to find out the volume rate flow we have to find out the velocity of each layer. So to find out the velocity of each layer, let us suppose that a random layer which is having some width of dr, let's suppose this layer have a width of dr and the radius of the layer is r. Okay, and this you can assume that this is a cylinder, this one, like that. Okay, so this is a cylinder, and this one, and the velocity of the liquid on the top point of the cylinder is v plus dv. This is v plus dv, and the velocity at this point is v. Okay, and the width of the cylinder is dr. So we can easily see the situation that this cylinder, this smaller cylinder which has a radius of r, is being pushed inside by the pressure difference of P1 minus P2. So we can say that the pushing force developed is P1 minus P2. Let us write down that it is P1 minus P2 into area of the cylinder is pi r square, small r, because we are talking about the cylinder which is having a radius of small r, this one. And this pushing force is being counterbalanced by the viscous force applied by the top layer, this one, and this viscous force Fv. Now the viscous force will be minus it would be minus neta into area. Now area of contact will be curved surface area of the cylinder, so it is 2 pi r L into velocity gradient is dv by dr. So we can write it down, we can cancel pi with pi, r with r, so we can write it down as delta p into r dr is equal to minus neta into 2l dv. Okay, and let us now integrate this term and let us apply the limits from 0 to capital R. Now we know when radius is 0, we are on the axis of the cylinder, and the velocity of liquid on the axis is v0, and the velocity of liquid on the circumference of the pipe is 0, because we can assume that the molecules which are just in contact with the pipe will be at rest. So this is the limit, and delta p into r square by 2 will be equal to, let us write it down as r square by 2 will be equal to 2 neta L into V naught. Now if we have substituted the limits as from 0 to small r, then the limit of, this is 2L, limit of dV will be from V naught to V. So in this case, delta P into R square by 2 will be equal to 2 neta L into V naught minus V. And we also know that V naught is equal to delta P R square by 4 neta L. So we can substitute the value of delta P R square by 4 neta L. So we can see that delta P by 4 neta L into R square is equal to V naught minus V, and this value delta P by 4 neta L is V naught by R square. So we can say that V naught minus V is equal to R square into V naught by capital R square. So this is, so V is equal to V naught is common, 1 minus R square by R square. This is the value of velocity of flow at a distance of r from the axis of the cylinder. Now we have to find out the volume rate flow. Now let us assume that some liquid, we know that some liquid will be flowing inside this width of the cylinder, this width. So the volume rate flow of this liquid will be equal to the area of this width, the cylinder, cylindrical width dA into velocity V. So dQ is dA. dA is 2 pi r into dr, and velocity is V naught 1 minus r square by r square. So integrating both the sides, Q, total volume rate flow, will be 2 pi V naught integration of r minus r cube by r square into dr, and the limit will be from 0 to r. So Q will be 2 pi V naught, and this is r capital R square by 2 minus capital R square by 4. So Q will be equal to pi V naught into R square by 4, in fact 2. Now let us substitute the value of V naught. V naught is delta P R square by 4 neta L. So V naught is delta P R square by 4 neta L. So Q will be equal to pi R square by 2 into delta P R square by 4 neta L. So Q will be equal to delta P pi r to the power 4 by 8 neta L. This is the required formula of volume rate flow through a pipe in the laminar flow. So in the next video we'll be discussing some more concepts on viscosity. Thank you.